İnniki çıkışçı alımımız Aybolek Amanmyradova. Aybolek Amanmyradova 2013 yılda Türkmenistan'ın Halkara Türkmen Türk Üniversitesi'nin matematika bölümünü utoran. Ondan sonra Baruch Kalaş'ta Master of Science statistikadan usatlığını alır. 2018 yıldan beri olsa Kaliforniya Üniversitesi'nin Berkeley'deki Kaliforniya Üniversitesi'nde Research Methodology, Statistics and Data Science uğruna doktoranturasını ediyor. Bugünkü çıkışının teması olsa Causal Inference. Ya da alıcık ütkaptır eden Statistical Causality mi?
How ikisem şoğlar. Alıcık ütkaptır madeni. Yani mani tuşa. Çağıranın için sağ olun. Başla vereyim mi?
Katılışınız için.
Sağ olun, sağ olun.
Bunu kameram yapayım.
Şöyle diyeyim. Şunki temam Causal Inference ya da Statistical Causality görüşünü diyalog. Türkmençe çek oldum, yani terminolojiye katı köp. 80-90%'ını Türkmençesini bilmem için İngilizce etmekçi. Yani sorularınız var olsa Türkmençe arkayın sorarım. Türkmençe cevap verecek olurum. Ulu tema Türkmençe bir sözlem bilen aytsam, sebebi mesela bir zadın, tebiği bir vakanın ya da cemiyetçilik ilimlerindeki bir vakanın sebebini statistika nuktay nazarından nädip bilip bolýar. Şu arada gayetçe görün vermekçi. Bu gatı ulu tema içinde edilen işler köp. Men gatı çalıp ve gayetçe bir vaktin içinde şu hemme temalar cemlep, metotları cemlep görün vermekçi, beter metotların içine, beter matematikasına için girmekçi değil. Okay. Okay, so what is the, just a second, let me try to, okay. So what is the motivation behind causal inference? The questions about cause and effect span centuries of thought. So here I wrote a couple of quotes from Greek philosophers, like the first one from Democritus. He says that I would rather discover one causal law than be the king of Persia. This is just an example, and mainly I think most of the research that is done are concerned with finding the cause mostly. And the causal questions span many disciplines. I wrote a couple of examples, but you can increase the number of these examples. An example from economics, for example, would be just one example. What is the effect of rebranding initiative on the level of customer loyalty? So you're asking a causal question. In fact, in 2019, three Nobel Prize winners in economics were awarded the prize for the experimental approach to alleviating global poverty, basically. They used experiments to answer a causal question. And an example from education would be, what is the effect of a particular teaching strategy or an educational policy on students' educational outcomes? Can I annotate this? Annotate it, yeah, okay. So an example from epidemiology and medicine would be assessing the effect of vaccine or a treatment on patients' health outcomes. An example from technology, user experience research or A/B testing. These are all experiments. And for example, assessing the effectiveness of an ad also would be a causal question. We can give similar questions from psychology, physics, chemistry, etc. So basically spans many, if not all, disciplines. Why can't I just use existing statistical tools? Maybe most of you are probably familiar with regression or a difference in means test or a t-test. So why not just interpret regression coefficients as causal effects? So the first and the major issue with that is, are you sure that your model is correct? So there is a famous quote by statistician George Fox, which says, all models are wrong, but some are useful. So when you run any statistical test, you make a lot of assumptions. And in this case, those assumptions are too strong for causal inference. And the meaning of causal is not made clear in regression. And regression coefficients are unstable due to Simpson's paradox, and I will explain what is Simpson's paradox in my next slide. Yeah.
Başlayın, hayal rakurlayın. Benim qadiyan ol imkan keşf etmek kıyrak olyada. Olyada o.
Bol bağışlan. Vallahi. Doğru aytsanız meni biraz çalıp kurlayandırın. Şöyle yana çalıp kurlasam yoşak olayın deb aytayım. Köp adam için statistika ekan qiziqildi, biraz iç hısqınç bolar deb fikir edip arasında kartonlar qo'shib qo'ydim. Shu karton men fikrimcha interpretation like ne deb ma'nini nahil chiqarganing barida deb fikir edem için bir ma'rifni avvalgi kulki bo'lsin deb qo'ydim. Masalan, here one says, someday I want to get married because studies show that married people are happier. And another point of view would be a smarter interpretation is that no one wants to marry an unhappy person. So he's meaning that there's just a correlation. Happy people want to marry happy people, that's why they're married. So just kind of a little detour. And from my previous slide, I mentioned Simpson's paradox. So what is exactly Simpson's paradox? It occurs when the direction of association between two variables changes when a third variable is included in your model. So I found this is an example from the web. It's not my work. This is here's the source. So a person analyzed the relationship between salary and neuroticism. So as you can see here, if no other variable is included, you can assume that there's a positive relationship between neuroticism and salary, which is counterintuitive. We would most likely think that neurotic people would not get paid as much. As you can see here, there's a positive correlation. However, if you include the education level of the employees in this equation, so as you can see, the blue is a high level of education, medium and low level of education. As you can see, education is positively correlated with both salary and neuroticism. So in this case, education is a compounding variable. It mediates the relationship between salary and neuroticism. So within each level of education, the higher the neuroticism, the lower the salary. So by controlling for education, by adding the education in this equation, we actually flipped the relationship between salary and neuroticism. Before we saw that it was positive. Now we see that by controlling for education, by including education in our equation, the relationship is actually negative. And this is one example of Simpson's paradox when the direction of association changed from positive to negative. Another example is, this is very recent, about race, COVID mortality, and Simpson's paradox by Donna McKenzie from UCLA. So again, this is not my work. So they analyzed the data, the most recent data about COVID from CDC. So here, it's probably not very visible, but this is the graph of cases by race and ethnicity. So this one is white, Hispanic, Black, and the others. And this is the graph of deaths by race and ethnicity. So this is white, Black, Hispanic, etc. So as you can see here, let me get the percentages. 35.3% of diagnosed COVID cases were white, non-Hispanic. However, 49.5% of COVID deaths occurred to people in this category, to white and non-Hispanic. From this perspective, we can see that we might think that coronavirus actually discriminates against white people, which is not what we were told in the media. We were told that more Black and Hispanic people were dying because of coronavirus than the white people. So what is happening here? And so of course, the elephant in the room is age. Since these two graphs do not look at the age, do not take into account the age, we might think that there's a positive, that white people die more than the others. But when we take into equation the age, it's not shown here, but when we look at the death rate in every age category and by race and ethnicity, we can see that in every age category, whites actually have lower case fatality rate than non-whites. The reason is simple, is that whites are older. So according to US census data, 9% of the white population is over the age of 75. By comparison, only 4% of Black people is over the age of 75, and only 3% of Hispanic people is over the age of 75. So basically, age here is the mediator variable between race and death from COVID-19. And so it actually, since the white people have a bigger population of older people, it seems like they're dying more. But in reality, when we categorize by the age groups, we can see that in each age group, actually the death rate for white people is always lower than for Black and Hispanic. This is another example of Simpson's paradox, when by including a third variable, the relationship changed. And why am I talking about Simpson's paradox again? How is this related to causal inference? This is to say that just regular regression, just taking regular regression without making any assumptions is not the best way to go to answer causal questions, because by adding just one other variable, you can flip the relationship. Okay. Another argument that we cannot just use existing statistical tools without making any other assumptions or without using more rigorous methods is a debate of correlation versus causation. There's a famous quote among statisticians by an unknown anonymous person that correlation does not imply causation. And we need to add here, correlation does not always imply causation, because sometimes it does. But overall, this is not to say that correlation is useless. Correlation is indeed useful when you're worried about prediction, when your research question is predicting some future value. In that case, correlation is very important. But if your question is why, answering the question of why, then correlation alone is not enough. So here's an example of the difference between correlation and causation. The first one says 100% of people who breathe die. This does not mean that if you breathe, you'll die. This is just a correlation, because if you breathe, it means you're living, and at the end of the day, you'll die. And here's an example of causation. 100% of people who don't breathe die. So this is actual causal relationship. If you don't breathe, you'll die. Another example, a very fun example, is attributed to Professor Yule, also statistician, according to Neyman, another statistician, just to give credit. So this example says that the number of storks per year nesting in small villages of a given country and the number of newborns in that village is associated. So the more number of newborns in the village, there tends to be more number of storks in that village. So if we think that all correlation association is causation, we might think that the storks actually bring newborns to people, but we all know that's not true. So it is clear there is no causal relation. So what is the third variable that mediates the relationship, that explains this association? And at a closer look reveals that the number of storks as well as the number of newborns reflect the size of a village. The bigger the village, the more the people, the more the number of newborns, and the bigger the village, the more the number of roofs for storks to nest. And so the actually number of roofs is explaining both the number of storks and the newborns. So this is an example of correlation is not always causal relationship. So this whole debate brings us to finding out methods specifically for explaining causal relationships, and how statistics approach this. It started with the starting point was potential outcomes framework, which I will very briefly explain, which was proposed by Professor George Neyman. He actually proposed this in his doctoral dissertation in 1923, and he's a founding father of the statistics department here at Berkeley. And then it was popularized by, so this is George Neyman, and it was popularized by Donald Rubin in his 1974 work of Harvard Statistics Department. And therefore, this the whole framework is called Rubin causal model. And in Rubin's belief, here's a quote. he says that there is no causation without manipulation. So the basis of everything that was done is the belief that there has to be human manipulation in order there to be a cause. And therefore, his mathematical formulation would be like this. Let's say I have n experimental units. This can be whatever you are experimenting on. This can be patients, students, or non-human objects. And let's say there are 2 treatment levels. It's binary, 1 for treatment, 0 for control. So let's say you're testing a drug. If you administer the drug to that particular patient, that will be 1. And if that person is in control group, by control mean no treatment. So you do not give the drug to compare. So that's your control group. And then you have the outcome of interest, right? So why are you giving the drug? What are you planning to find the causal effect of that drug on, right? So that will be your outcome of interest, and it is in most cases denoted by the letter Y. And in a hypothetical world, we believe that there are 2 versions of the outcome for each unit, for each subject. We believe that there is an outcome for that subject under treatment and under control. So these 2 values are called potential outcomes, or in some literature, counterfactuals. So again, this is a hypothetical world. In real world, this would never happen. You will not give one person both treatment and control. You can only give a person treatment and another control. So you would, in actual research, you would observe only one of these. But let's say we could do this in hypothetical world. The causal effect is the difference between potential outcomes, average difference between potential outcomes. So let's say I can observe both values for each person, and then the average difference would be my average treatment effect. So this is my target parameter. This is something that I'm trying to measure, but I can't measure it, therefore I need estimation. If I could measure it, there would be no field of statistics. So statistics is all about uncertainty and measuring, trying to estimate something that I can't actually observe. So the actual average difference between potential outcomes is something that I would never be able to observe. So I need to find a best method to estimate it. And here comes cell research. So this is, again, basis for all of the methods that were developed. The idea is that I want to estimate this as close as possible, as accurate as possible. So there are different types of studies that that researchers do to answer causal questions. Of course, the first thing that comes to mind is running an experiment. There can be completely randomized experiment or stratified randomized experiment. In a completely randomized experiment, this is, I think, mostly done in labs, in lab environment, where you have subjects or clinical trials where you have your subjects and randomly assign those subjects to treatment and control groups. In this case, there are several different tests, statistical tests that you can use. The first one is Fisher randomization test. Here's Ronald Fisher, very important figure in statistics. The idea, it uses sharp null. So if you're familiar with statistical tests, you have the null hypothesis, and then you are testing that hypothesis, right? So Fisher randomization test puts very sharp null hypothesis, or some people call it a strong null hypothesis, where the hypothesis that you're testing is that every single potential outcome for each person is actually equal, and then you're testing it. You can use different test statistics to test this hypothesis. It can be simple difference in means, or t-test. It can be Wilcox and Rank-Sum, Kolmogorov-Smirnov statistic. So I'm giving out these names in case you would want to use this method and would want to use it in your own research, but I'm not going to actually explain all of these methods. Another test is Neyman's test, which puts a little more weaker hypothesis, where the null hypothesis is no longer that all of the potential outcomes are equal, it's just the average of them is equal. What is stratified randomized experiment? Again, this is a very important figure in statistics, George Fox. A quote by him says, block what you can and randomize what you cannot. By block, he means stratify. So basically, instead of completely randomizing treatment and control groups, so what is the idea behind randomization? I want treatment and control groups to be balanced and comparable so that all of the other variables other than the treatment would be like age or gender, or if that's a disease, some, I don't know, some test results, whatever. So I want those to be comparable in both treatment and control groups. So when you do complete randomization, sometimes it may generate undesirable treatment allocation. So the covariates may be imbalanced. So let's say there is a significantly more number of females in treatment group and significantly more number of males in the control group. So we don't want that. We want them to be balanced. So in that case, stratified randomized experiment is useful when you can just stratify. Let's say I gave an example, gender. Let's continue with gender. Let's say I stratify by gender, male and female, and then I randomized among males and I randomized among females. In that case, my treatment and control groups would be balanced based on gender. Again, so you can use Fisherian inference, as I explained here, Neymanian inference. You can also use a regression adjustment. So by regression adjustment, I mean running a regression. It's a statistical tool where you try to predict Y based on some covariates. In this case, Y outcome, run a regression on your treatment variable plus your covariates like your gender, age, etc., etc. However, it is suggested to add an interaction term between treatment and covariates. So by interaction term, it means the product of treatment times every single one of your covariates. It improves asymptotic efficiency. What this means is basically it's a statistical term to say that your inference would be more reliable. And under completely randomized experiment, it is also suggested to use, some people call it Eichler-Huber-White standard errors or sandwich standard errors, because it gives a consistent standard error estimation, and therefore your test statistic would be more reliable. And so these are suggestions by, I think he proposed, he was a Berkeley statistics student. He graduated in 2013, and he proposed that in his doctoral dissertation. All right, that was the experiment. Now, other kinds of, sometimes experimenting is not possible. It's a very famous example. Let's say, does smoking cause lung cancer? It's a causal question, but I can't randomly assign people to smoking. That's unethical. So in this case, the only thing I can do is observe. In observational studies, the main issue here is that the treatment is not randomized. And if you remember from Rubin, he says, there is no causation without manipulation. Since we are not manipulating anything here, we're just observing, we might think that causal interpretation is not possible. Then a simple difference in means is unbiased. Unbiased is here in statistical sense, which means the expectation of the estimator does not equal the parameter. So it's not the other kind of bias, it's statistical bias. And so if you can, you need to randomize, because randomization balances the distribution of the potential outcomes across treatment and control groups. Now, if we can't do that, can we give up on observational studies? Is it not possible? It is possible, but you are making very strong assumptions that you need to be aware of. So a strategy in observational studies is to use the information of the pre-treatment covariates. So in this case, if smoking is treatment, so what is the information I know about that person before he started smoking? So that I use that information, and I assume that conditioning on those covariates, which I denote as X, so conditioning on those covariates, the selection bias will reduce. So basically, you can use, again, regression controlling for the X values. This seems easy, right? Okay, so I just need to run regression of the outcome on the variable that I think is the treatment, because this is an observational study, and plus some baseline covariates, and interpret the coefficient of the treatment as causal effect. This seems easy, right? Well, if you do this, most people will critique it and might not accept your results. So you need to use more rigorous methods. And here comes the idea of propensity scores. So what is a propensity score? It was proposed by Rosenbaum and Rubin in 1983 paper, and it is one of the most cited papers in statistics. So the propensity score is defined as the probability of getting treated given all of the baseline covariates. By baseline covariates, again, I mean maybe demographic information like age, sex, and like family income, etc. How am I doing on time?
You have 5 minutes.
Oh, okay. Okay, so using propensity scores, I can control for the propensity scores in my regression. So that's preferred. Now we come to the causal diagrams. So causal diagrams were introduced by Judea Pearl. He's a computer scientist from UCLA, and he's actually a Turing Award recipient. Here's his picture. He introduced causal diagrams as a powerful tool for causal inference and empirical research. So basically, he proposes to use a diagram like this. It's a very simple one. Let's say this is treatment, and this is outcome, and these are baseline covariates. And these are very important when you try to convey your assumptions and the model that you're using. A very powerful visual tool. And he also proposed, so the main issue with the previous one, with the method Rubin causal model, is that he proposed to use as many baseline covariates as possible into, let's say you're using a regression. So he proposes to use as many baseline covariates as possible. But Judea Pearl gave 2 toy examples. So these are not real world examples, but given toy example, he showed 2 instances where not controlling for X is actually better. So one is called M bias example, one is called B bias. I'm not going to explain everything, but with these 2 toy examples, he showed that actually not controlling for baseline covariates is better for inference. And therefore, he says that the idea of including as many possible variables as possible is not always the right way to go. So that's one research area. So other research areas in the field of causal inference is called instrumental variables. This is where you cannot actually randomize the treatment itself, but you're randomizing a proxy. It's very like popular tool in economics. Then there's a problem of non-compliance. Let's say I have a perfect, I'm running a perfect clinical trial. I randomized, I did everything perfectly, but then the subject, let's say my treatment is taking vitamin D every day, but then my subject does not do it in the treatment group. So that person does not comply with the treatment. Then what? Is my experiment ruined? Is my trial ruined? What can I do? So there are statistical tools to deal with non-compliance, and there's a whole research area for that problem. Another research area is what's called superlearner and targeted maximum likelihood estimation. And superlearner is what I think is pioneered by Professor Mark Vanderlaan, again from Berkeley. So this is a machine learning tool to select the model and the algorithm for you, the best model that fits your data. So this is not like neural network. No, I shouldn't say that. So your input would be your data set and a library of potential algorithms and models that you want to test. Let's say, okay, I have a data set. Should I use a logistic regression? Should I use a linear regression? Should I use a neural network, or should I use some other machine learning tool? So instead of you deciding this, superlearner decides it for you using giving you a algorithm with the lowest cross-validated loss. Okay, now I'll give you very brief examples that I did for a couple of my classes, answering a causal question. So the first example is diabetic retinopathy study. So what is diabetic retinopathy? Is the loss of vision in people with diabetes. And this study was testing whether laser treatment on the eye would help stop vision loss. And they had two types of laser, xenon laser and argon laser. So they had actual two treatments and one control. And so the research question here is there significant difference in survival of the eye given treatment and control? So I'm comparing whether xenon laser treatment is actually helping the eye or not, or argon laser is actually helping the eye or not. So we used superlearner and targeted maximum likelihood estimation. We run the analysis in R. And here's the difference between blue one is control, pink one is the treatment, between xenon laser and control. So in this example, we can see that the 95% confidence intervals overlap. So this suggests no statistical significant difference in treating the eye with xenon laser versus not treating it at all. And this is the example of argon laser versus control. So the 95% confidence intervals do not overlap, which suggests that the argon laser actually improves the vision in statistically significant sense. And final example is about data set, about the research question of whether there's a causal effect of text message reminders on adherence to anti-malarial treatment in Tamale, Ghana. So this trial took place in, again, Tamale, Ghana, African country, between July and November 2011. So what they did was health service vendors advertised free mobile health information on flyers to individuals purchasing anti-malarial treatment. And if they agree, study staff enrolled them to participate in text reminders. And then the messaging system randomized. So this is, again, randomized control trial. So if they agree to participate in this trial, they randomize it, assigned to text message reminders or no reminders at all. And if in treatment group received text reminders, 12 hours intervals for 72 hours, basically. And the outcome of interest would be, so then they went and took a questionnaire and self-reported adherence based on the follow-up interviews, whether they adhered to the taking the pills or not, whether the text message reminders actually helped or not, basically. And so we had 18 baseline covariates, which I'm not going to discuss. And this is the causal diagram. A stands for treatment. Since treatment was randomized, there is no effect of baseline covariates on the treatment. So there's no line here. And we used R software. We used three methods to estimate the causal effect. Simple substitution, which is the difference in means. This is a method called IPTW, which I'm not going to discuss. And this is targeted maximum likelihood estimation. And so based on all of the three methods, the p-value is more than significance level 0.05. So what this suggests that there's no statistically significant difference in probability of adhering to the anti-malarial treatment, whether you send them a text message reminder or do not send them. This has suggests policymakers to look to other avenues of improving treatment adherence. Okay, so takeaways. It's not possible to remember everything, but if you can just take away a couple of things, it would be that correlation does not imply causation. So keep this in mind when reading any kind of statistics. Do not take it at a face value. Do not think, okay, if they say that in this group there is a more chance of something, whatever. Do not just think that there's a causal relationship. And don't forget about Simpson's paradox. And when you're reading a paper or a study, always ask, how did the researchers decide what variables to control for? That is very important because, as we learned from a couple of examples, adding another variable may completely change the relationship. So that's something to look for. Thank you. Sağ olun.
Çok sağ ol benim için. Türkmenlere ayetlerdim. O kapitler bir navolun sonundan roman toronton bir soruya diye düşünmedim. Aynı girdim ya artık girdim mi dipten. Şu an gel bun ki şu an ayet verdi yani causation var mı yok mu? Correlation, causation demek derler düşünüyor yani. O lazım technical rak bolan ortlar ýöne statistika barada sorularyňyz bolsa jogap berin.
Şu kendi technical etmejek bolşum değil.
Şey.
Zadrak kolaytyana.
Şimdi data analiz için hem yani bir R programmasını ulanyan diýdiň. Köplenç R ulanyan ya başga programmalar ulanyan mı?
İn köp R ulanyan. Ýöne meselem käbir sapaklar için state diýen bir zat var, state diýip ýazylýar. Onu köplenç epidemiologiyada ýa-da ekonomikada köp kullanylýar. Ol ýöne diýel industriýada işlejek bolsaňyz data science diýerler. Onda R köp kullanýar, bilen Python da kullanylýar. Python'dan R'ın tapawydy R diňe statistical software, diňe statistik üçin bolan üçin onda has köp package'lar, has köp metodlar, datlar statistika kullanylýar. Python general language, onda sen application'dan gurulýanlardan bol diňe statistik üçin de bolan üçin onda biraz az ýöne esasan hem computer scientistler like machine learning radetýänler Python has köp kullanýarlar diýilýär.
Industriyada men R köp ulanýar diýip bilemokan ulanýan badyr elbetde, ýöne köplenç Python ulanýan kadýanda. Mümkin. Hani o başga diýen oturar ýatyp berler da. Akademiýaň hani köplenç stat ulanýar, ýöne hatam ösüp barýan döwletlerde stat programmaty gymmat bolandan R ulanýar. Hazır R nemeti sophisticated package'larda.
R mut bolan üçin şonsam öwren her kim access, her kim zat edilýär.
Ýöne R azıkça sürmürak da stat wara Windows.
Öwrenmesi, zat ýok, GUI'si ýok. Statyda sen basyp knopkalara basyp bilen da kod ýazmak.
Bir analiz edeninden soň causation çykdy. Hani causation öwrenýär, hani şu cause edýär diýip. Ondan soň haýsy testleri etmeli, yani bir sürü test verdim da ya her edýän ulanýan statistiki metodyna görä testler ütkeýärmi? Ya şu causation hakykatdan hem barmy ýa-da ýokdugyny, yani spurious effect mi ýa bir correlation mi? Şonu näme anyklap bolýar?
Bu soru men şu insan kulan biri Judea Pearl diýip causal diagram şu diagramlar görkezipdim. Men pikrimçe şanyana spirit relationship mi dämi, şu ululuklaryň arasyndaky aragatnaşyk doçunmy dälmi şonu görkezmek üçin men pikrimçe gowy tool sebäbi visual görýän we pikirlenmäni ymtyltýar saňa sebäbi sen hemme variable'laryň hemme ululuklaryň arasyndaky çyzyklary etmeli bolýan we çyndan hem diýeli şonuň arasyny şoňa sebäp bolýan bolanok şonu pikirlenmeli bolýan. Ýöne statistik metod şon ebensoň estimation'da hani şol nähil ululukda causal effect näçe ululukda dugyny estimate etmek üçin kullanylýar. Ýöne haýsy ululuklary, haýsy variable'lary sen modelyňa goşmaly etmeli, ony ingo bilýän adam domain expert. Diýeli şu etýän eksperiment diýeli ekonomist etýärmi? Şu variable'laryň arasynda aragatnaşyk bady teoriýa görä, öz literaturasyna görä ingo bilýän adam domain expert ekonomistiň özü. Ýok, men haýsyny goşmalygyny bilemok, data adaptive bir zat barmy özü çıkarar ýaly haýsy variable'lar goşmaly da. However, stepwise regression diýip bilinýän random forest ýa-da başga machine learning tool'lar bar. Saňa sen pikirlenmezden saňa haýsy variable'lar goşmaly da maslahat berip bilýän tool'lar bar.
Teşekkür. Göl alyp barýan işin näme diýerler? Experimental experiment edýänmi ýa theoretical statistician mi?
Sonra özüm theoretical diýip hasap edemok. Yani biraz applied işi has gowy görýän. Experimentalistim däl, köpçe observational data bilen işleşýän. Şonu hasam gyzykly görýän sebäbi observationda iň kyn tarapy çykýar da randomized experimentda köp uje research edilen, köp soraga jogap berilen observational study täze çykyp ol barada has research köp edilýär. Öz ilmi işim hasam köp zat nested hierarchical data diýilýär. Meselem bir misal bilen diýeli okuwçylar gadyň içinde nested bolýar. Klaslaryň içinde klaslar, mekteplaryň içinde mektepler, districtlaryň içinde nested hierarchical bir näçe levelli datalar bolýar. Köplenç statistikada näme assume edilýär. Her bir diýel adam ýa-da her bir data bir-birinden independent, bir-birinden baglanşyk diýip assume edilýär. Meselem diýeli regressionda iň uly assumption şu. Ýöne mes datada ol assumption dogry gelen ok, sebäbi bir klassak okuwçylar bir-birinden independent correlation bolýar. Bir mekdepde klasslar bir-birinden correlated bolýar. Uşa şataýda abyşly statistik tool bolanok, uşa ütgaşyrak toollar etmeli bolýar. Ina şon ýanyk datadaky causality sebäp baglanşygy barada research meni interesting.
What is your current research or study?
Dowam şon ýanyk hierarchical datada näde causal effect çykaryp bolýar, anyň intra-class correlation coefficient diýilýär. Şo taýdaky clusterlar barmy ýokmy, şon ýanyk temalarda.
Şonu ýazyp barýar, düşnükli. Muhammed Oral commented edipdir forada, and R is not usually very scalable with increasing data sizes diye. Hani data data olsa yani gigabaytlar bitse terabayt olsan R cevap berýänçe naharik kelmeli bolýan, kofçy kelmeli bolýan olam kompýuteryň götürdi da.
Olam dogry. Hem adam plus minus we olam dogry. Ýani arın plus men kymça haskyp. Ýani olam dogry comment.
Araz Tomaja, what is the best way to report COVID spread? Total positivity that depends on number of tests or percentage of positive tests, i.e. rate of increase.
What is the best way to report COVID spread?
What is the best way to report COVID spread? Total positivity that depends on number of tests. Hani Trump diýer, biz köp test edýäs, sonuçta pozitif kan çykýar, or the percentage of positive tests. The rate of increase.
Okay. I would think that the rate of increase, because if you just report the number of positives, it would depend on your population, and it would depend, as Trump says, more testing, more results. But if you report the rate of increase, I think that's more useful.
Did I understand you correctly regarding your study related to anti-malaria? Did you ask subjects to participate in the study and then randomly assign the ones who agreed to participate into treatments?
So, so men edenim secondary data analysis, men edenim experiment run etmedim. 2017'de edilen dat men data post analyze ettim. So o şolong edenim zadet ýalar health vendorlara barıp ya da farmasiylara barıp şu treatment alýarlar da, dermanlar alýarlar. Şonda daşynda durup durlar şu adamlar, hani zadet ýalar flyer berip text message reminder şunu goşlasyn gelýär, gelen okmy diýip flyer berýärler. How consent eden soňlar randomize etýärler.
Anonymous attendee, do you have any advice to the non-statistician when working with a statistician? Data cleaning, power analysis, etc. People sometimes may tell you their project goals and ask you sample sizes.
I see. Suggestion for a non-statistician working with a statistician. Okay, so men maslahatım statistician köp adam batmak diýär, data analysis. Uja hemme rad etdi, hemme iş netdi, research netdi. Data analysis wagty gelen okay şunu ran edip berýär. Ondan has ön konsult etmegini maslahat berýän sebäbi senin eden eksperimentin aslında sen soragyna jogap bermänen biler in statistical sense. Şonuň üçin hatta hasymyň şu researching ya da experimenting design staging da consult etdim. Sana edil şu research question answer etmek üçin nähili data gerek, nähili şekilde randomize etsen o ya da randomize etmesen garap nähili data ýygnamagy, näde design etmeliň barada da maslahat berer. Şu başından consult edip başlamagy maslahat berýär.
Köp hökümetler public datalarını goýýarlar diye, publicly accessible. Turkmenistan için data analiz edip gördüňizmi? Bilýän government non-official data source'laryňyz barmy?
Gynasagam ýok, edibem görmedim, şoňaýsam gözläbem görmedim, şoň üçin bilemok.
Do you research on GDP statistics?
No, I don't.
You don't?
I don't.
All right. In data science, about 60 to 70% of task is cleaning data and adjusting it to data accordingly. So Python would be more useful in that case. Everyone can analyze data once it's ready. Challenging part is preparing it. soru Wamka. Once data is ready, you can just apply your statistical model. Another advantage is Python packages are more customizable.
I agree how I can comment bilen agree, you know.
Düşünüyorum. Soru yok. Yani cleaning data dana meňorty statistician bilen habarlaşdynmy biri?
Özü data ýygnaýan bolsa, o consult etsin. Yani diyelim secondary data analysis etýän bolsa, baý bolan data set analyze etýän bolsa, onda uşa başga tema.
Düşünüyorum. Do you recommend any good books on introduction to statistics?
Gatygy soru. On introduction to statistics, suggestion'ım yok. Yani eğer introduction to causality, causal inference, güdletler gelse, şu juda yaparlığın zat kitaplar var, causality diye bir kitabı var, biram Book of Why diye bir kitabı var, şolar maslahat berýän. Başında has filosofiki näme üçin şu soru gerekdigini, bir statistika da garaz. Şu zatlaram düşündirýär. Statistika introductory bir kitaba aklıma gelenok.
Bir PhD programmasına näme ýyldyňyz? Hani ýa-da şurda PhD etjeklere näme maslahat berdiňiz?
So, kiçiligimden men statistik okujak diýip ulalmadym. Matematik okasym gelýärdi. Statistika barada känbir popularnydygyny, känbir möhümdigini bilen okudym üçin maýsam universitetde öwrümem. Ýöne universitetde okuýanmasam matematika professor bolasym gelýärdi. Okaýan döwrüm känbir gaty theoretical ýerde, men biraz applied data bilen işleşesim geldi. Şol sebäpden soň statistika switch etdim we pişmanam da, hatda bir kim aýtýan bilemok bir statistikaçy diýe, statistika barada iň gowdatlaryň biri her kimiň backyardyny oýna bilýän diýdi. Garaz, sen statistika okasaň, sen isleseň educational research et, isleseň political science research et, isleseň tech industriyada işle, policy analysis, garaz sen health care'da işlebilýän biostatistik hatda fieldama. Şu tarapyny maslahat berýän. Ýöne bir tarapam kompýuter bilen maraňy bolmaly. Köp işin kompýuterde işleýär, bir adamda köprak programming var. Okujaklara programming öwrenmeklerinden maslahat berýän. Şeýdik gelim, yani öňünden statistik okujak diýip gelmedim, ýöne pişmanam-da. Has applied, has real life datalardan işleşýänim üçin bolýar.
Bu arada soruya batyrdyp bir master's degree üçin math ýa-da data science haýsy maslahat berýän?
Math ýa-da data science, okay.
Maksad näme onu ýazmandyr hani?
Şu maksady gerek. Eger akademik iş işlejek bolsaňyz, data science master'y convert data bolar demek. Eger master PhD edecek bolsaňyz, math maslahat berem. Hatda admission master's kiper degeni PhD-de başlap bilersiňiz. O aýry mesele. Ýöne industriyada işe girecek bolsaňyz, data science okasaňyz hasga bolar eken.
Data science diýä urum, artificial intelligence, machine learning uruny işlemek.
Artificial intelligence, machine learning davasanız in computer science med bilersiňiz master'yňyzy. Data science hat applied bolar, bilmedim köp AI, machine learning öwrederlermi? Computer science masters has köpek knowledge verýär sosyologlarda.
Bir sorular niye uğradı? Are there biases in addition uğradılar öyle kardeşim? Are there biases in the data sets that also affect the resulting statistical models? If so, how to remove them? Biaslar hani?
Are there biases?
How to remove hani bias dediğinde de şu biasları nerede ayırmalı ya da azaltmalı?
Düşündüm. So gurrun selection bias bolýan bolsa diýeli observational data var. Sen prosto data observe ettin, sen hiç bir treatment'dan adım yok. Yankı değişmeli smoking causes lung cancer or not. Observational da ondan şu taýda smoking'da selection bias var. Smoke etýän adamlar fundamentally smoke etmeýänlerden ütköş başga sebäpler bardyr. Şoň üçin lung cancer outcome'daky difference diňe smoke edip etmeýände baglamak dogry bolanok. Başga sebäplerden bardyr, ikisine de contribute etýän. Şol ýagdaýda modelini da hem smoking'a hem lung cancer'ına ikisine de takdir edilecek başka ululuklar, variable'lara modelini da koşmalı. Şon yani da selection bias'ı ayırıp bilýäňiz. Başka bias köplenç estimator var da bolýa. Mesela bir misal verdim. Käbir ýagdaýlarda diňe difference in means ýa-da diňe t-test kullanmak bias bolýa. Ol ýagdaýlarda prosta başga metodlar ullanýmaly. Metodun özü bias bolýa. Very ýagdaýa gara ýükseýär denähili alyp çykmalydyňyz.
Awa. Gaty için maglumat gerek bolsa siz bilen habarlaşdyrar bolarmy?
Hawa, ştat email ýazmaly kelimeli.
İşleşen hani mümkün olsa täze slide açıp e-mailini ýazyň.
Şeydeýin.
Başkalar bilen işleşmäne da açykmy bilemok. Ya biri onu demek için demeti gerer. Bir soruwa ýene gelýän. Mental models tonkudurlar trend boldy diye. But do you have models that you can use consistently at your work, such as confirmation bias, etc.?
Näme work patwer bolup
mental models diýär, tonkudurlar trend boldy diye. Batır için
mental model.
Trend bolupdyr. Şo barada maglumatyňyz bar.
O zatlar köplenç statistikada näle o bias'da model sözüm bir hil olar maňa hasy psychology neuroscience alyp geldi. Men bilýänim confirmation bias sen bir zat öwrenende öňden bilýän bolsaň şoňa görä ýykyn bolýan. Edil statistikada näme many ifadyny bilemok.
Uzunlanýan bir ýa-da rollanýan bir modeliňiz barmy diýip soraýan.
Ýa-da ullanýan modelim köp ullanylýan regression elbette. Gaty robust manysynda köp datalara içine sığdyryp bilýär. Köp adam ullanýan şol diýip pikir etken. Linear regression we outcome continuous bolan ýa-da logistic regression we hatful metodlar elbette var. Mesela LASSO regression, ridge regression diýip zatlar var. Mesela LASSO dadetýär hem variable selection etýär, ýa-ni soraňyz ýaly haýsy variable'y include etmeli diýip bil soraw bolsa, LASSO regression diýip bir zat var. Hem saňa variable'lar select etýär, hem saňa regression coefficient'lar estimate edip berýär. Bular elbette model based. Model based demek bir topar assumptionlar var. Ýa-ni diýer independence diýdik, normality assumption ýene bar. Onyany assumption edesiňiz gelmese machine learning toollar var. Neural network diýip bir zat var. O конечно black box. Sen eger coefficientlary interpret etjek bolsaň o can useful däl. O saňa prediction üçin bolýar. Başga da gözleşdirseňiz random forest diýe gatköp toollar var. Her soraňa görä. Soraň näme diýip çykardym. Şan ýanyk toollar var.
İnsan soru gördüňizi 10 ýyl içinde nirde görýäňiz?
Batı soru. Doğrusu aýtsam edilken bilemegim. Gutoramsoň entak PhD'mi gutormadym. Optionlar, faculty positionlar bolupdylar. Assistant professor diýip giribilsem. Edil Amerikada biraz her kim bilýän job market faculty position biraz kynrak. Şoň üçin men optionlarmy açyk goýasym gelýär. Bilemek industriyada ýa-da industriýa bolmasa da research institutionlarda quantitative research scientist atapmynda bolupdylar. Netide.
Düşünükli. Statistikada da näme kompetitiv mi gaty?
Kompetitiv.
Akademiýa. Düşünükli.
Wow.
Aybolek. Bu köp sawalmany beren gurulmaňyz üçin.
Sağ olun size.
Sorularınız olsa şu Aybolek at Berkeley.edu yazıp bilersiňiz.